We defined the weak and the strong topology in the spaces of CR differentiable maps between manifolds by using local charts. But we are interested in providing a definition that does not depend on local charts, an intrinsic definition, because that's going to be useful, for instance, in applications, and indeed it's going to make our arguments simpler. If we have to depend all the time on the use of local charts, the arguments are going to be unnecessarily difficult. So we want to define the weak and strong topologies, trying to avoid, if possible, local charts. And first, we are going to consider the continuous case, the case of continuous maps between manifolds M and N. First, let's consider the weak topology in the space of continuous maps between two topological spaces, X and Y. We are going to define the weak topology by giving a subbase, and the subbase consists of the sets of the form A n sub k v, whose elements are continuous maps such that the image of K is contained in V, where K is a compact subset of X and V is an open subset of Y. In this way, we have a topology in the set, in the space of continuous maps from X to Y. This topology coincides with the weak topology in the space of continuous maps from M to N, where M and N are manifolds. And it is not difficult to check out. This is an alternative definition. And indeed, this topology that we define, which is the weak topology when X and Y are manifolds, is the topology of uniform convergence. We have that the limit of a sequence of continuous maps is equal to F if and only if the sequence converges uniformly to F on every compact subset. Okay? Indeed, since it's the topology of uniform convergence, if we have that X is compact and Y is a metric space, we can define a metric that actually induces this topology. Indeed, what happens is that our space of continuous maps is going to be a metric space, and the topology associated to the metric space is going to be exactly the weak topology. This metric is the following. The distance between F and G is the maximum when X belongs to the in this case would be to X. Here there is a mistake, okay, where X belongs to big X, of the distances between Fx and Gx. Okay, this is well defined because F and G are indeed continuous maps, and the source space X is compact. Okay, and obviously this convergence for this metric is just uniform convergence. Okay, which is expected because uniform convergence on compact sets, when the domain is compact, is just uniform convergence. So what we see is that if X is compact and Y is a metric space, then the space of continuous maps from X to Y is indeed a metric space. Okay, that and this the topology of this metric space is the weak topology, or the strong topology if you want. If X and Y were manifolds, would be the strong topology, because in the case in which the source space is compact, both topologies are the same. Obviously here we don't have a strong topology because X and Y a priori are just topological spaces. Okay, so the metric, we have something that it is interesting. The metric is complete if Y is complete, okay? Because what happens is that if you have a sequence, a Cauchy sequence, and you fix a point x in the space big X, okay, then it is obvious that the sequence of images of X by the elements of the sequence Fn, this is going to be indeed a Cauchy sequence in Y. But in that case, this Cauchy sequence has a limit because the space Y is complete. And the definition of a complete space is just that every Cauchy sequence has a limit. So using that Y is complete, we get that there exists the limit when n tends to infinity of Fn applied to X. And indeed, it is not difficult to check out that the limit when n goes to infinity of the distance between Fn and F is 0. And indeed, it's not difficult to check out that F is continuous. So we have that every Cauchy sequence in our space of continuous maps is convergence. It's convergent, sorry. So this space over here is a complete metric space. Okay? Okay, we know that when we have the space of continuous maps between X and Y, X is compact, and indeed Y is a complete metric space. Then this space is also a complete metric space. But the issue here is that we cannot assume that X is always compact. For instance, when we consider the weak topology in the space of continuous maps between X and Y, or M and N, M is not necessarily a compact manifold. So we would like to give a complete metric even in the case in which X is not compact, a complete metric that indeed defines the weak topology. Okay, that's our goal. Very good. So first, let's talk about the hypothesis here. What does it mean to be locally compact? A space is locally compact if every point P in X has a neighborhood system consisting of compact sets. Indeed, in particular, every manifold is locally compact. So for manifolds, the two conditions are just one. We are going to require that our manifold is second countable. And what do we have when X is second countable and locally compact? In that case, we always have an exhaustion of our topological space X by compact sets. So there exists a sequence Ki or Kn of compact subsets of X such that every compact subset is indeed contained in the interior of the following one. Okay, So we are going to suppose that this exhaustion by compact sets exists, right? Now let's try to define the metric. So we are going to consider di, a sort of distance between f and g, where f and g are indeed continuous maps from x to y. And this sort of distance, because it's not a distance, it's not a metric, it's going to be the maximum when x belongs to ki of the distance between fx and gx. Okay? This is well defined because ki is indeed a compact set. Okay? And it's not a distance because it's possible for two continuous maps to be equal in ki without being equal. So it could be 0, but still f being different than g. It's totally possible. Anyway, we are going to define now our metric. The distance between f and g is going to be the sum from I equal 1 to infinity of 1 divided by 2 to the power I times di of f and g divided by 1 plus di of f and g. Sure, this is well defined. The denominator here is never 0 because di is greater or equal than 0. This expression over here is smaller or equal than 1. So the whole term here is smaller or equal than 1 divided by 2 to the power I. So this sum over here is always convergent and indeed is smaller or equal than 1, right? And this is indeed going to be a metric because it's clear that the distance, this distance is 0 if and only if all the di's are 0. Okay, so it's 0 if and only if f and g coincide in ki for every ki, so if and only if they are equal. It's clear that it's symmetric and it satisfies the triangular inequality because all the i's do, and then it's a simple calculation. You can check it out. Okay. Besides that, we have that the limit when n tends to infinity of the distance between fn and f converges to 0, in other words, fn converges to f, if and only if all the limits when n tends to 0 of the di applied to fn and f converge to 0. So this topology is going to be the topology of uniform convergence in the ki's. And since the ki's are the compact success of an exhaustion, it's the topology of uniform convergence on compact sets. So this metric over here gives a structure to the space of continuous maps between x and y of metric space, and the induced topology is indeed the weak topology, right? Besides that, the metric is complete because if you have a Cauchy sequence for this metric, then it's going to be Cauchy with respect to the di's. So you're going to have convergence in every ki, and so you have a limit in the union, and it is clear that the fn's converge to f. So in this way, we have that the space, the topological space of continuous maps between x and y, in which the topology is the weak topology, is a metric space that has a complete metric. And that's really interesting. In particular, for instance, it has the properties of a metric space. For instance, every point has a countable neighborhood system, okay? We want to apply these results to the case of manifolds, okay? Sure, we are always going to consider manifolds that are Hausdorff and second countable, so this is not going to be a problem. M is going to be second countable and locally compact because every manifold is locally compact. So the issue is, okay, is M a complete metric space? And what we need is defining a metric, a complete metric, that defines the same topology that N has, okay? And this is possible because we can define a Riemannian metric G in the tangent space by using, first of all, local charts, okay? If you have U, which is contained in M, and you have, that's the domain of a local chart, the differential is indeed an isomorphism between the tangent space of U and the tangent space of B. Something like this, where n is the dimension, n is the dimension of our manifold. And in that way, here we can use the usual scalar product, and this is going to provide a Riemannian metric in the tangent space of U. And we can paste these metrics, these Riemannian metrics, to obtain a Riemannian metric which is defining the whole tangent space just by using partitions of unity. Once we have defined the Riemannian metric, if we consider a path gamma, okay, a C1 path, we can actually calculate its length. The length of gamma is the integral between 0 and 1 of the norm of gamma prime of x. This norm is actually the norm defined in the tangent space of n at the point x, the norm provided by the Riemannian metric. And gamma prime of x is just the differential of gamma at x applied to 1, okay? This is indeed a tangent vector of n at the point x. And so it makes sense to consider the norm provided by the Riemannian metric. Okay, in this way, we can define now the distance between 2 points. It's just going to be the infimum of the length of the paths gamma that connect the C1 maps, indeed, the C1 maps gamma that connect the points x and y. Okay, we are going to require that gamma of 0 is x and gamma of 1 is equal to y, and of course that gamma is a C1 path. And in this way, we obtain a metric, okay? Of course, there is an issue here, and it is that this metric is not a priori complete, okay? We defined a metric, but maybe it's not complete. Let's see how we can make it complete. Sure. What's the problem here? The problem is that we could have a sequence of points, okay, such that this sequence is bounded, okay? For instance, there is a point P such that the distance between P and Pn is smaller than 1 for every n. But these points Pn could be actually in a Cauchy sequence, but they don't converge. This could happen. And indeed, if we have that the closed balls of the following type, the point consisting of the points Q in N, such that the distance from P to Q is smaller or equal than R, if these balls are always compact for any choice of P and R, okay, then we have that the metric is complete. Okay. So we have to ensure that these closed balls are compact. Here the problem is that we have a closed ball center at P that contains all these points, and so it's not compact. And how we can do this? When we actually calculate the integral, the length of the paths from P to one of the points in the sequence, this integral is bounded. But there is a way of making it bigger, which is multiplying the Riemannian metric by a function that is big. If you multiply by 2, then the length is going to be multiplied by 2 and so on. So what we want is considering a function defined in n and with values in the positive real numbers that grows very, very fast. And in that way, we are going to ensure that the length of the paths going from, for instance, P to points that are, let's say, close to infinity, to the infinity of the manifold, we're going to ensure that the length of all these paths is actually very big. And in particular, that these closed balls are indeed compact. So we have to define a function rho that grows very fast. And in that way, by considering rho times G, where G is the Riemannian metric that we just found, we obtain a new Riemannian metric that actually is complete. The new metric is complete. In the new metric, the Cauchy sequences converge. Okay? So we can interpret any second countable Hausdorff manifold, okay, as a complete metric space. And the topology, of course, is a topology of the manifold M. So what we have is that if M and N are manifolds, then the space of continuous functions from M to N, this space topologized with the weak topology has a complete metric. There is a metric such that this metric defines the weak topology. And it's very simple because M is locally compact and second countable. We only consider manifolds that are second countable and Hausdorff. And N can be interpreted as indeed it's also second countable and Hausdorff, and it can be interpreted as a complete metric space. And so by using the result that we had in this case, we get that this space over here has a complete metric. In particular, it has the properties of a metric space. One of them is that every point, in this case every function, has a countable neighborhood system. And this is going always to happen through the weak topology. So the weak topology is always first countable, right? In the current lecture, we saw that the space of continuous maps between differentiable manifolds with the weak topology can be interpreted as a complete metric space, a property that is useful in applications. Unfortunately, the analogous property is not true for the space of continuous maps with the strong topology. But even so, we would like to see if such a space has another interesting structure that could be useful in potential applications. We will see that that is indeed the case, and that the space of continuous maps with a strong topology is indeed a very space. That's going to be the subject of our next lecture. Thank you for your attention.